In this video we're going to continue learning about series. In the last video we learned about what a series was and what it meant for a series to converge to a number. We also learned a few tests to see whether the series converged or not, and in this video we're going to just continue with propositions and theorems that will give us other tools to test whether a series converges or not. And in this proposition we have a sequence that's greater to 0, and what we're going to do is we form another sequence, c sub n, with the division between the sequence a sub n divided by the sequence p sub n. And what we're going to do is calculate the limit of this sequence c sub n, and let's say it converges to L. And if this L is greater than 0, then what we have is that a sub n will converge if and only if b sub n converges. So let's try and do the proof. We have that the limit when n tends to infinity of c sub n, this is the limit of a sub n divided by p sub n, equals to L. So using the definition of limit of a sequence, which if you don't remember you can check out previous videos, then we know that for every epsilon greater than 0 there exists a natural number n such that the sequence a sub n divided by p sub n minus our limit is smaller to epsilon, and this happens for every natural number greater to n. So now we can use the definition of an absolute value and have that minus epsilon is smaller to the sequence minus our limit and smaller to epsilon. Now adding L on both sides, we have L minus epsilon smaller to a sub n divided by p sub n smaller to L plus epsilon. Now if we remember our hypothesis, we had that b sub n was greater to 0, and because b sub n is greater than 0, then we can multiply by p sub n, and we would have L minus epsilon times b sub n smaller, this sign doesn't change because of this, to a sub n, and smaller to b sub n times L plus epsilon. So now from this first inequality we have that b sub n is smaller to a sub n divided by L minus epsilon. And here, so that this sign doesn't change, we can just take epsilon small enough so that L minus epsilon is greater to 0. Because if we remember, L was already greater to 0. So if epsilon is smaller to L, then this is valid and this sign won't change. So from this inequality, using the comparison test we learned in the previous video, we know that if the series of a sub n converges, then the series of b sub n converges. And now from this other inequality, we have that a sub n divided by L plus epsilon is smaller to b sub n. And from this one what we have, again using the comparison test, that if the series of b sub n converges, then the series of a sub n converges. If you don't remember this comparison test we're using here, then I recommend you go check out the theorem and the proof from a previous video. Now that we have this proposition, we're gonna start with a definition that will help us a lot in not only solving exercises, but also in proving other theorems. We define a geometric series. It's a special type of series formed with a and r, two real numbers, and the series is a times r to the power n minus 1. And this series starts from n equals 1, so the first power of r, the s sub 1, would be a times r to the power 0, so the first one is a. I am remarking this because sometimes it starts with n equals 0, and the series is formed by the sum of a times r to the power n, and they are both geometric series and they represent the exact same thing. So what's important about this series is that it converges and its sum is this one. It's a divided by 1 minus r, and it will converge even if r is smaller to 1. So now that we've defined geometric series, let's try and prove the next theorem. This is another test we can use in solving exercises, and it says that if I take the nth root of the nth element in our sequence, and this root is smaller to 1 for every number n greater to some k, a natural number, then our series will converge. So the thing is, if I can find this k such that for every n that's greater to k, this happens, then my series will converge. And now if I find the k such that for every n greater to k, this happens, now it's greater or equal to 1, the nth root, then our series will diverge. Let's try and prove it. Let's call this one number 1 and number 2 and start with proving number 1. So here what we have is that the nth root of a sub n is smaller than or equal to alpha, where alpha is just a number smaller to 1. So then from here we have that a sub n is smaller than or equal to alpha to the power n, and this will happen for every n greater to some k. And then the sum of a sub n, the sum we want to see if converges, using this will be smaller than or equal to the sum of alpha to the power n. And then this is the same as saying the sum from n equals 2 instead of 1 up to infinity of alpha to the power n minus 1. And we know because of a geometric series that if it starts with n equals 1, then my sum is this number here. So now the sum from n equals 1 of something, let's call it a sub n, is equal to the first element, a sub 1, plus the sum from n equals 2 of a sub n. And if we know that this sum is 1 over 1 minus r, or sorry, a over 1 minus r, then we know this sum because this is an element in our sequence. So then the sum from n equals 2 of a random sequence a sub n, if the sum from n equals 1 is equal to this, will be a over 1 minus r minus the first element. And this is something we can use here. So this one would be, this is a geometric series, we can write it as adding from the first one and then subtracting the first element. And the first one is alpha to the 1 minus 1 is alpha, let's just write it like this. So then this sum is a geometric series and we know exactly to what it converges, because here the number a would be 1. So then this is 1 over 1 minus alpha to the power 0 is 1. And so we know that our series is smaller to this number, but then this is only telling us that our series converges. And now I'm gonna leave you the second proof as an exercise, because it's very simple and you have to use the same sort of things that if here we're using that if our series is smaller to another series that converges, then our series converges, that is the comparison test. And in the second case, we're gonna have to use the opposite, that if our series is greater to a series that does not converge, then our series will diverge. So for this you have to remember that the geometric series will converge if this is strictly smaller to 1. So using that and the comparison theorem, I think it's pretty easy to leave this as an exercise. And now we can continue with this other theorem. We have a sequence that's greater than 0, and the limit of dividing one term with the previous term gives us this number L. And so we have two things, that if L is smaller to 1, our series will converge, and if it's greater to 1, our series will diverge. Something to notice is we know nothing about L equal to 1, and we'll see later that when this happens, we might have sometimes that our series will converge and some other cases where series will diverge. Let's go on with the proof and start with the number 1. We have that the limit when n tends to infinity of a sub n plus 1 divided by a sub n is equal to a number L smaller to 1. So what this is telling us is that there exists a number alpha smaller to 1 such that a sub n plus 1 divided by a sub n is smaller to alpha for every n that's greater or equal to some number k. So then a sub n plus 1 is smaller to alpha times a sub n. We're multiplying by a sub n, and we can do this because a sub n is greater to 0 for all n. But then this happens for every n greater to k, so what we're gonna have is also that a sub n is greater to alpha times a sub n minus 1. And so writing this alpha like this, we have that a sub n minus 1 is smaller to alpha times, and a sub n minus 1 is smaller to alpha times a sub n minus 2. And so when we get to the number k, we're gonna have that this is smaller to alpha to the power n minus k, because if you think about it, here we have alpha squared and n minus 2. Here we have alpha to the power 1 and n minus 1. So here we have alpha to the power n minus k times a sub k. And so the sum, and here we'll have from n equals to k, because we know these inequalities are valid for n greater to k, up to infinity of a sub n will be smaller to the sum from n equals k to infinity of alpha to the n minus k times a sub k. A sub k does not depend on n, so we can take it as a common factor outside the sum. We have a sub k times the sum from n equals k to infinity of alpha to the n minus k. And now using that alpha is smaller to 1 that we said here, we know that this will be some number, but it's convergent, because this can be written as a geometric series, so it doesn't matter what the actual value is, but we know it converges. And so our series is smaller to another one that converges, and so the sum, we can now add the other k terms we were removing here, and it's okay because it's still a finite sum of a sub n converges. Now let's try and prove number 2. Now we have that the limit when n tends to infinity of a sub n plus 1 divided by a sub n is equal to some number L greater to 1. So from this we get that there exists a number k natural such that a sub n plus 1 divided by a sub n is greater to 1 for all n greater than or equal to k. And so multiplying here by the denominators, we get that a sub n will be greater to a sub n minus 1, and a sub n minus 1 will be greater to a sub n minus 2, and so on. They all be greater to a sub k. And so here we have that the limit when n tends to infinity of a sub n is greater to the limit when n tends to infinity of a sub k. But as this doesn't depend on n, this is just a number, then the limit of a number is the number itself. And we said that a sub n was greater to 0 for all n. So this is different to 0. And then as the limit is different to 0, our series diverges. This is also a theorem we saw in the last video, so I recommend you go and check it out. Now that we've finished with these few theorems, let's put them to test in some examples. Let's say we have the series from n equals 1 to infinity of 1 over n. In this case, our sequence a sub n is 1 over n. So what we're going to do is study a sub n plus 1 divided by a sub n, so we can use the previous theorem. A sub n plus 1 divided by a sub n is 1 over n plus 1. This is a sub n plus 1 divided by 1 over n. And this is n divided by n plus 1. And now we have to calculate this limit. The limit when n tends to infinity of n divided by n plus 1. And now this is something we've done many times before, multiply and divide by n. If you don't remember about this, I recommend you check out the videos on limits of sequences. So this is the limit of n divided by n divided by n plus 1 divided by n, because we are putting these two together here and then these other two together here. So then this is the limit of 1 over 1 plus 1 over n. And then when n tends to infinity, this goes to 0 and we have 1 over 1 and the limit is 1. Let's go again to our theorem. We had that the limit was L, and we knew what happens when L was smaller to 1 and n greater to 1. But in this case, for L equal to 1, we know nothing, so we actually can't say anything. To know whether this series converges or diverges, we need to do some other tests. But in this case, the sum diverges. Now let's look at another example. We have the sum from n equals 1 to infinity of 1 over n to the power p, where p is just an integer. Again, what we need to do is study a sub n plus 1 divided by a sub n. So this is 1 over n plus 1 to the power p divided by 1 over n to the power p. This is n to the power p divided by n plus 1 to the p. And we can just write this as n divided by n plus 1 to the power p. And now this, when n tends to infinity, goes to 1. So again, as before, there's nothing we can say about the convergence of this sum, but it's important for us to know that we have two cases. This sum converges when the absolute value of p is greater to 1, and it diverges when the absolute value of p is smaller than or equal to 1. The previous example was when p was equal to 1, and we said that it was a divergent. Let's continue with another example. We have the series of n divided by e to the power n. So again, we're going to study a sub n plus 1 divided by a sub n. This is n plus 1 divided by e to the power n plus 1 divided by n over e to the n. This is e to the n times n plus 1 divided by e to the n plus 1 times n. Using the distributive on the numerator, we have e to the power n times n plus e to the power n. And all this divided by e to the n times e times n. So now we can write it as e to the n times n divided by e to the n times e times n plus e to the n divided by e to the n times e times n. Now, these two terms cancel out, and here this one cancels out, and so we have 1 over e plus 1 over e times n. So the limit when n tends to infinity of a sub n plus 1 divided by a sub n is the limit of 1 over e plus 1 over n times e. The limit of the sum is the sum of the limits, and this first term does not depend on n, so we have 1 over e plus the limit of 1 over n times e. And this is clearly 0, so the result is 1 over e. Now, 1 over e is approximately 0.368, and this is smaller to 1. So then we know that this series converges. As a last example, but I'm gonna leave it as an exercise, try to determine whether this series converges or not. It's the sum from n equals 1 to infinity of e to the n divided by n. The calculations are gonna be very similar to this one because it's the inverse. And now we're gonna finish the video with this very important theorem. It says every absolutely convergent series is convergent. This is something we actually already saw. It was a corollary in a previous video, and what it means is that if the sum of the absolute values of a sub n converges, then the sum of a sub n without the absolute value converges. This is the corollary we saw. And it says, in addition to this, a series is absolutely convergent if and only if, notice that if and only if means that both ways are valid, the series formed with the positive terms and the series formed with the negative terms are both convergent. Let's look at the proof. We have a sequence. And what we're going to do is, as we have to work with the positive and the negative terms, we're going to separate the sequence into two. So we have a sequence formed with all the positive and the zeros, and a sub n with a minus sign is going to be 0 if a sub n is greater than or equal to 0, and a sub n if a sub n is smaller to 0. So here we have all the negatives and the zeros from a sub n. That is, if our sequence, this is the 0, if our sequence is doing something like this, then the positive one would take all these positive elements and also these two that are 0, and the negative one would take all these negative numbers but also these ones that are 0. Now, as I said before, we have to prove an if and only if. We have to say that if both the positive and negative converge, then the series is absolutely convergent. Let's do that one first. we have that if the series of the positives and the negatives converge. Let's see what happens with the one with the absolute value. Here I'm not putting all the extremes in the sum, but they are always from n equals 1 to infinity. This sum can be written as the positive terms stay positive, and then the negative terms with a minus sign. That way the negative terms are positive and they are adding up to the positive ones to form the absolute value. Now we can separate this into two sums minus the sum with the negative terms. And we know these are both convergent series, so then the sum of two convergent series is just the sum of two numbers, and it's smaller to infinity. So then a sub n is absolutely convergent, the series. That means that the sum converges with the absolute value. And now let's see the arrow the other way. We have that if the sum of a sub n with absolute value converges, we know, because of the corollary, that the sum without the absolute value converges. So then we can write the sum of a sub n positives as 1/2 the sum of a sub n plus the sum of a sub n with absolute value. But then this one converges and this one converges, so it's a number plus another number divided by 2. It's just another number. And the same with the one in the negatives. It is 1/2 the sum of a sub n minus the one with the absolute values. And again, this has to be smaller to infinity. So then the sum with the positives and the sum with the negatives both converge. And that is what we were trying to prove with this theorem.